In 15.4, we're going to move on from our double integrals, and then we're going to be computing triple integrals. So common applications for triple integrals would be to compute the mass of an object. So from physics, remember that mass is equal to volume times density. Now, whenever we integrate, you can view it as adding a dimension. So if we're in double integrals, we can compute volume. If we add another dimension or another integral, we could look at that as being the density. So our triple integrals can be used to compute mass. And then later on in this semester, we'll look at computing what we call center of mass, which is the point at which our object will balance. So this will be important for those of you that are doing engineering and you want to figure out where your supports should go. It's usually in the center of the object, but if the object doesn't have a constant density, then the support would not be in the center of the object. It would be where that center of mass is. We're also going to use our triple integrals to find volume. So it'll be another way to find volume, similar to finding an area with a double integral. When you find volume with a triple integral, the integrand is simply 1. So here's the idea. The region that we're going to be integrating with respect to, instead of having a two-dimensional region R, as we did with double integrals, we're going to have a three-dimensional volume D. And the idea is that we're going to be taking our little volumes and we're going to add them all up so that we can compute our fourth dimension, which is usually mass. Looking at a close-up of one of these boxes or volumes, it's going to give us some delta V, some volume delta V. So if we simply take the limit as delta goes to 0 of this Riemann sum, where our function is going to be some function W written in terms of x, y, and z. So we're taking W times delta volume. As delta goes to 0, what that's going to give us is it's going to give us our triple integral over our region D, which happens to be a volume. And then we'll have our function in terms of x, y, and z, and then this would be a dv. We have to be careful about the order in which we integrate. So the typical order is that we want to keep the inner integral with respect to z. Our limits of integration for z will be functions of x and y. Once we integrate with respect to z, that variable z is gone, and then our middle would be y, where y is a function of x. Once we integrate with respect to y, then y is gone, and we're left with our outer integral integrating with respect to x, and these would be our constant limits of integration. It's not always going to be in that order, but typically it's going to be dz, dy, dx. And that's what's in this theorem 15.5 when we talk about triple integrals. So in this section, we're just going to deal with the variables x, y, and z. In later sections, we're going to look at polar coordinates, looking at angle measurements instead of our typical x, y, z. So here we have what we just talked about, our triple integral over some region D. We're going to integrate this volume, which we will break up into dz, dy, dx. However, it may not be in that order. It depends on what you're given. So let's look at the simplest case. In example 1, we have a solid box. And this solid box is our volume D. Remember, D is a volume. It's bounded by these planes, x is equal to 0, x is equal to 3, y is equal to 0, y is equal to 4, z is equal to 0, and z is equal to 1. So the density of the box is represented by this function, 4 minus z. So we have a density function. That's our integrand. We want to find the mass of the box. I'm going to go ahead and sketch this region. Again, apologies for my sketches. When we look at the planes that are bounded by the x value, we have x is equal to 0 and x is equal to 3. So all I'm going to do is go to 0, and I'm going to say that this is 3 here. And then my y's go from 0 to 4. So that would be planes parallel to the xz axis from 0 to, oops, don't want a big one, to 4. And then my planes z, they'll be the bottom and the top of my box, would be these horizontal planes, z is equal to 0 and z is equal to 1. So building my box, I have this following shape here. So there's my box. The sides are made up of the planes, the vertical planes, x is equal to 0, x is equal to 3, y is equal to 0, y is equal to 4, and then the bottom and the top are made up of the horizontal planes, z is equal to 0 and z is equal to 1. So I have this box. This is my region D. And my limits of integration here is going to be x values from 0 to 3, y values from 0 to 4, and z values from 0 to 1. Oops. These are constant limits of integration, so technically the order that we set up our integral really doesn't matter. Okay, so our mass. And I'll use the usual order where the outer is going to be with respect to x. So x is going to go from 0 to 3, and then I'll do y for the center, 0 to 4, or the middle. Z is going to go from 0 to 1. My integrand is my w function, 4 minus z. And then the order is going to be dz, dy, dx. Again, I can change the order around since I have all constant limits of integration, but I'll leave it in this order. Our inner integral with respect to z is going to be 4z minus z squared over 2, integrate from 0 to 1. So it's similar to that of a double integral. All you're doing is integrating inner to outer, and at each integration you're getting rid of a variable until you just are left with a number. So putting in 1, this is going to be 4 minus 1/2, which would just be 7/2, and then minus the 0. And I am not going to show all those steps. I'll just put in 7/2 dy dx. We have 7/2 y. And when we evaluate that integral, it's going to be 4 times 7/2, which would be 28 over 2, or 14, and then minus 0. This is simply 14 dx, which would be 14x. When I evaluate it from 3 to 0, I get 42. So very similar to double integrals, they're just longer. And you do have to be careful with the order that you're integrating with respect to. Not only do you always have to end with constant limits of integration, you have to make sure that if you do have variable limits of integration, that you get rid of that variable. So we'll look at an example of that. In example 2, we want to evaluate the triple integral. D is going to be the solid tetrahedron. So if you don't know what a tetrahedron is, it's a three-dimensional triangle. It's not a pyramid, because a pyramid has a rectangular base. It has a triangle base, and all the sides are triangular. So this is a 3D triangle. It's going to be bounded by these planes. X is equal to 0, y is equal to 0, z is equal to 0, and x plus y plus z is equal to 1. So we're going to compute this triple integral over our region D. The integrand that we're given is z. First thing we need to do is we need to figure out what D is. That will determine our limits of integration. I'm going to go ahead and sketch this region. You don't have to sketch the region, but it really helps when you're trying to figure out your limits of integration. So x is equal to 0 is the x, or the z, y, or yz plane. Y is equal to 0 is the xz plane. If you wanted to think about that as these two planes, and they actually go parallel here, kind of like that. So you're looking at these two vertical planes. One is the xz plane, one is the yz plane, but they're going to go into the negative z values as well. And then z is equal to 0 would be this xy plane at the bottom. So we have almost bounded, but notice that the z values go up to positive infinity, and that's where this plane is going to come in. When we look at this plane, let me see if I can erase some of this. Oops, the yellow's not going away. Oh well, the yellow will stay. So when we look at the plane x plus y plus z, I need to sketch that. So remember, the strategy of sketching a plane is, first of all, I want to find the x-intercept. So I set y and z equal to 0, and I have x is equal to 1. So I'll pretend like this is 1. Then I have the y-intercept would be putting in 0 for x and z, and I have y is equal to 1. And then I get z is equal to 1 as well. So I have this plane, and the bounded region, I'll put that in green, is going to be this. This is my volume that I'm looking at. That's my D. So what are my limits of integration? Well, it's a little bit difficult when you're in 3D space. So what I'm going to first do is I'm going to look at the XY plane and go back to what I did with double integrals, and I'm going to look at this region R, just in the XY plane. All right, so we have x is 0, y is 0. Remember, when we're in the xy plane, what we do is we put in 0 for z. So if I put in 0 for z, I have x plus y equal to 1. I have this line, when x is 0, y is 1. When y is 0, x is 1. So I have this line that crosses over the x and the y axis. Now, since I know that my region is bounded by x is equal to 0, y is equal to 0, then I know that I'm just dealing with this segment here, this triangular region. If I look at x as being my constant limits of integration, then I can see that my x values, if I were to go in the direction of the x-axis, are going to go from 0 to 1. So I can see that my x values go from 0 to 1. Now if I look at my y values, if I draw a line parallel to the y-axis, I see that I start at 0, and then on this slanted line, that would be my largest y value. So I'm going to take that equation, x plus y equal to 1, solve it for y, to get y equal to 1 minus x. which means my limits of integration for my y are going to go from 0 to 1 minus x. Now I have to figure out the limits on z. Well, if you look at the original problem, we're told that we're looking at z is equal to 0, and then x plus y plus z equal to 1. Those are going to be my limits of integration for my z. But I have to solve for z in the x plus y plus z is equal to 1. Think about this. I'm going to go from A, and now I'm going to draw a line in the three-dimensional D region, parallel to the z-axis. I'm looking at values for z from 0 to whatever the equation of this plane is, and the equation of this plane is z equal to 1 minus x minus y. And those would be my limits of integration for z, from 0 to 1 minus x minus y. So when I evaluate this triple integral that I was given, I'm going to have my x on the outside, those constant limits of integration. Next is y from 0 to 1 minus x. And then next would be my z from 0 to 1 minus x minus y. My integrand is z. I have a dz, dy, and dx. This integral is going to be z squared over 2, evaluated from 0 to 1 minus x minus y, dy dx. So now when I plug in 1 minus x minus y into the z squared, I have 1 minus x minus y squared over 2 dy dx. I'm going to pull out the 1/2 into the front. So I'm just looking at, maybe we'll do this off to the side, 1 minus x minus y squared. So you could just multiply these out. I can't integrate it the way it's written. But I'm going to notice something. That remember, I'm going to be integrating with respect to y. And I notice that this is actually 1 minus x in parentheses minus y. 1 minus x in parentheses minus y. So if you recall the product formula in algebra, when you take two values that are the same, and they're both in this case minus minus, and you multiply it, it's the square of the first minus 2 times their product plus square of the last term. So I'm just going to go ahead and write this as the square of the first term, which is the 1 minus x. You don't have to, you can multiply the whole thing out. You'll get the same answer. Minus 2 times their product, so 2 times 1 minus x times y, plus square of the last term, so square y, to get y squared. Again, this is just algebra trick. Don't have to do it. You could multiply the whole thing out, end up with the same answer. So now when I integrate with respect to y, notice that this first term, I wonder if I'll have space. The 1 minus x squared, there's no y there, so it's a constant. So the antiderivative will be 1 minus x squared times y. So I have a minus 2 times 1 minus x, that's all constant, times y. So it's going to be a y squared over 2. The 2 will cancel, and I'll have minus 1 minus x y squared. And then plus y to the third over 3. when I plug in 1 minus x for y, in the first term it's going to be 1 minus x squared times 1 minus x, which would give me a 1 minus x to the third minus 1 minus x times 1 minus x squared will give me another 1 minus x to the third plus 1 minus x to the third over 3. And then plugging in the 0, each one of these terms goes away. With the 1 minus x to the third, those would cancel. And I think I'm going to take out the 1/3. So this is going to be a 1/6 integral from 0 to 1, 1 minus x to the third dx. So that's super nice. If you can kind of guess what the antiderivative would be, that's fine. I'm going to do a substitution. I'm going to let u equal 1 minus x. So my du is equal to negative dx. And then if x is equal to 1, then my new limits of integration would be u is equal to 0. If x is equal to 0, then u is equal to 1. This becomes 1/6, 0 to 1, u to the third times negative du. So I can bring that negative out into the front, but also notice my new limits of integration go from small to large, from 0 to 1. So I could also decide to change my limits of integration by switching. That would become a negative and the negatives would cancel. I would simply end up with 1/6, integral from 1 to 0 of u to the third du. But you didn't have to. You could have left all the negatives in there. So the antiderivative, 1/6 u to the fourth over 4, integrating from 1 to 0. That would give me 1/6 times 1/4, or 1 over 24. Now double integrals are long. We're adding another integral, so of course they're going to get longer. A lot of these computations are very tedious. So let's look at another example. In example 3, we want to find the volume of this prism D. It's in the first octant. It's bounded by these planes that are given here. First thing you should note is we're finding a volume, not a mass. So remember, when we find volume using triple integrals, what we're finding is an integrand of 1. Now this is a prism, so to find the volume of a prism, I could simply use geometry. So let's think about what this shape is. Excuse the siren in the background. Okay, we're looking at the first octant, so x and y are greater than or equal to 0. My z values go from 0, because it's first octant, to, notice that it's bounded by the plane z is equal to 5. So I'll just put a 5 here. And there's going to be some plane. That's where it's going to stop. Now, it's also bounded by the plane y equal to 3 minus x. So that's going to be a vertical plane. When x is 0, y is 3. When y is 0, x is 3. So it's this vertical plane coming up. And then we have our prism. I have my sad looking prism. Okay, that's better. So geometrically, what you do to compute the volume of this prism is you would take the base, which in this case the base is this triangular region in the xy plane. So let me go ahead and sketch just the XY plane. Similar to our last example, we would have this triangle. The base is 3, the height is 3. So when I look at this geometrically, and I compute the volume of this prism, it's going to be the area of the base, which is 1/2 base times height, because it's the area of the triangle. And then we multiply it by the height of the prism, which is 5. It looks like that's going to be 45 over 2. So I didn't even have to use calculus, but let's go ahead and do this with a triple integral. I have to determine my limits of integration. I already have the xy plane sketched there. So let's just say my x values are going to go from 0 to 3, which means my y values are going to go from 0 to the y value on this line, which is just 3 minus x. So my y values are going to go from 0 to 3 minus x. Well, now when you look at the three-dimensional sketch, my z values, if I draw a line parallel to my z axis, are just going to go from 0 to 5. In this particular case, both x and z have constant limits of integration. So when I set up my triple integral, I either have to end with z on the outside or x on the outside. However, y is written in terms of x. So no matter the order, as long as I end with constant limits of integration and I evaluate the y before I evaluate the x, because remember, when we integrate, at each step we're getting rid of a variable. When I integrate with respect to y, I'll still have that variable x because it's in the limit of integration. So then if I integrate with respect to x, I will be getting rid of my x. So one way we could do this is still have the x on the outside, 0 to 3, go y from 0 to 3 minus x, and then z from 0 to 5. Since it's a volume, integrand is going to be 1, so this is simply dz, dy, dx. And that would be the usual order, and that's completely fine. However, the only requirement here is that I end with constant limits of integration and I do y before x. So I could also change it so that my z is last. And then go x in the middle, and I could start off with my y and go dy, dx, dz. Okay? So when I integrate with respect to y, I have a x in my limit of integration, so I'm going to end up with an expression with x's in it. But then when I integrate with respect to x, those x's will go away, and then I'll have my constant limits of integration at the end. So you're free to rearrange. You just have to be very careful. I'll just leave it like that. And now when I integrate with respect to y, I get y evaluated at 3 minus x and 0. The 0 will go away. So this is a dx dz. Integrand is now 3 minus x. Integrating with respect to x, I get 3x minus x squared over 2. Oops, this is a 3, sorry. Okay, evaluating when x is equal to 3 gives me 9 minus 9 over 2. And then I have a 0. So 9 minus 9 over 2 is simply 9 halves. So integral from 0 to 5 of 9 halves dz, and we get 9 halves z evaluated from 5 to 0, and then that will give me 45 over 2, which is exactly what I found when I did this geometrically. So let's go back up to the original before I kind of changed the order and I left it as dz, dy, dx. Do we get the same answer? So if you were to integrate in the first order that I had written, you will find that you also get 45 over 2. Again, the caution here is that if you have a variable limit of integration, such as this x here, then we have to integrate that particular integral before we integrate with respect to x. So for example, let's just say that I changed the order so that my x was first and my z was on the outside. So I had 0 to 5, 0 to 3 minus x, and I had 0 to 3. So this would be a dx, dy, dz. That is not correct. Yes, I do have constant limits at the end, but notice that when I integrate here, and I'm not going to do the integration, when I integrate this inner integral with respect to x, that means I'm getting rid of the variable x. However, when I integrate with respect to y, I'm putting back the variable x, which I can't get rid of now because I've already integrated with respect to x. So this particular order will not work. Let's do one more example. We're going to find the volume of a solid bounded by the parabolic cylinder y equal to x squared and the plane z equal to 3 minus y and z equal to 0. So I'm given these z values between 3 minus y and z equal to 0. So it looks like I have my limits of integration for my z value. I just have to figure out x and y. All right, so let me think about this shape. And I'm going to look at this parabolic cylinder y equal to x squared. Okay, so if we're looking at y equal to x squared, let me look at this shape in the xy plane. This is simply a parabola opening upward, right? But it goes on forever. So there's no bound there. When I look at this parabola in the three-dimensional space, again, you get to be lucky enough to see my crazy drawings. Same thing's going to happen. These x and y values are just going to continue to grow. And this cylinder, remember, think of those level curves. It's still going to continue up, and it's going to continue down to the negative z values. So what I'm going to do is now look at my z values to figure out what kind of bound I'm going to have. Well, I'm bounded by z is equal to 0, so that would be the xy plane. So I can stop there. And then I'm bounded by the plane z equal to 3 minus y. Ew. Well, when y is 0, z is 3. When z is 0, y is 3. So there's this plane that comes down. What this shape is going to be is, so we have this bound at 3 that comes across. What this shape is it's going to be this wedge. Think of a doorstop. And I know this is my sad drawing. Where here's the base, the flat part of my doorstop. And then it slants up to where it intersects the z-plane at 3. So we have this wedge shape. What I'm going to do is I'm going to look at just the XY plane. Remember, did we also have this bounded by y equal to 3? And I'm going to figure out my limits of integration with respect to x and y, and then I'm going to look at my z values. I can look at my x values as being my constant limits of integration. So this shape, this region R in the xy plane, the upper function is y equal to 3. The lower function is y equal to x squared. So I have an upper and a lower. That tells me my integration with respect to y will be variable, x will be constant. So if you look at where my x values are, which would be when I set those two equations equal to 0, so we're just solving x squared equal to 3, so x is equal to plus or minus the square root of 3. So negative square root of 3 and positive square root of 3, those would be my limits of integration for my x value. And then my y values, again, I'm just going to draw a representative line parallel to the y-axis, tells me that my lower limit is x squared, my upper limit is the 3, the y is equal to 3. So negative square root of 3 to positive square root of 3 would be x, and then y would be x squared, upper is 3. So I have my limits of integration for x and y. X is constant, y is variable, so y has to come before x. Let's look at my z values. Well, I'm already told that z is equal to 3 minus y and z is equal to 0, so I already have my limits of integration for z, but which is the upper and which is the lower? Going back to the 3D graph with my z values, the lower is 0. The upper would be the point on this plane z equal to 3 minus y. So my z values are going to go from 0 to 3 minus y. So notice that I have a y in the limits of integration. That tells me I have to integrate with respect to z before I integrate with respect to y. So when I set up my limits of integration, x is going to be the outer, I'm going to have z be the inner, y is going to be in the middle. And it was a volume, so my integrand is 1, and the volume here is going to be x, negative square root of 3 to square root of 3, y is going to go x squared, lower limit, 3 upper limit. So once I've evaluated with y, I'll have an expression with x, but when I evaluate with respect to x, it'll be gone. The inner is going to be my z, 0 to 3 minus y. dz, dy, dx. The integrand is 1 because in the beginning I was asked to find a volume. Now I could integrate this the way it is, but whenever possible I like to include 0 as a limit of integration. It's going to cut down on my computation. So you notice with this wedge, the volume from x is equal to the negative square root of 3 to x is equal to 0 is the same as the volume from 0 to square root of 3 because of symmetry. So because of symmetry, for my limits on my x, I'm going to go from 0 to square root of 3, but then I have to multiply this volume by 2. You don't have to. I just don't want to put negative square root of 3 as a limit of integration if I can help it, and I can because of the symmetry. This is the integral that I'm going to be evaluating. Alright, so the integral is just going to be with respect to z, so it's just z, evaluated from 0 to 3 minus y, And that just becomes 3 minus y. So now when I integrate with respect to y, it's going to be 3y minus y squared over 2 all right. Oh, this is going to give me a little bit of a headache. So if I put in 3, I end up with 9 minus 9/2 minus 3x squared minus x to the 4th over 2. Well, I guess that wasn't that bad. So it's 9/2 minus 3x squared plus x to the 4th over 2. And integrating with respect to x, I have 9/2 x minus 3x to the 3rd over 3, so just x to the 3rd, plus x to the 5th over 2 times 5, or 10. Plugging in the square root of 3 gives me 2, and then the 0 would make everything go away. So it's just 2 times 9 square root of 3 over 2 minus 3 square root of 3 plus to the 5th, 9 square root of 3 over 10, I believe. Let's see, I can combine the 9 square root of 3 over 2 by multiplying top and bottom by 5, 45 plus 9. Oh, and the 3 square root of 3. So if I find a common denominator and combine everything, I think I get 24 square root of 3 over 5 after reducing, but you guys double check me on that. Okay, that was fun. The last thing we're going to look at is changing the order of integration. All right, so the directions say that we want to write this in the order dz, dx, dy. So the current integral is dy, dx, dz. When I look at my limits of integration, I'm doing y first, so I could see that my y values are going between 0 and 3x plus 3. My x values are constant, -1 is lower, 0 is upper, and my z values are also constant, 0, lower, 5, upper limit of integration. So I want to take this and I want to write it in terms of dz first. So z is fine. It's the dx dy that I'm going to have an issue with. And the reason why is because our limits of integration for y are not constant. If I end off with y, this has to be constant. So the dz is okay. I'm just looking at the dx dy, which means I'm just going to look at the xy plane. X goes from 0 to -1. The y values go from 0 to 3x plus 3. So if x is 0, y is 3. This is what I'm looking at here. I I want to change these limits of integration. I want to have y be my outer, which is what we did in the previous section. What we want to do is we want to take the equation y equal to 3x plus 3 and we want to solve it for x. So we're going to subtract 3 and we're going to divide everything by 3 to get x equal to 1/3 y minus 1. So now my limits of integration for my y values are going to go from 0 to this y value here, which is 3. And now my x values, think about drawing a line parallel to your x-axis. The smallest x value here corresponds to the line 1/3 y minus 1. The largest x value is 0. My x values will then be 1/3 y minus 1. The upper is 0. So the z values will still remain as 0 to 5. My integral will now be the outer value from 0 to 3. Remember, we were supposed to write the outer with respect to y. And then with respect to z, I'm going to have 1/3 y minus 1. 0 would be my upper limit. Or x, sorry, did I say z? And then the z would be 0 to 5. This would be dz, dx, dy. Okay, scroll all the way to the bottom here. Recall that when we were working with double integrals, we could find the average value of a function by computing the double integral and multiplying by 1 over the area of the region, R. So we can also find average values of a function. I'm not going to do any examples here. It's the same idea. You can find the average value of a function using triple integrals. But instead of multiplying by 1 over the area of the region, since our triple integral is a volume, it's going to be 1 over the volume of our region. But it's the same idea. So that's it for this section. Next, we're going to be working with triple integrals in what we call rectangular and spherical coordinates. So we're going to look at kind of combining them with polar coordinates.